This video is focusing on wave interference. So to follow along in your notes, we would be looking at section number 3, and the title of that section is Interference of Waves, Mechanical Resonance, and Standing Waves. So we'll be looking at both part A and part B, and we'll be looking at how two waves move across and interfere or collide with each other. So we're going to start off with what's called constructive interference. Now, we first want to remind you that, again, we analyze sound waves in terms of a transverse wave. So we'd be describing how interference occurs in a transverse pattern. But you have to remember that sound actually travels as a longitudinal wave, and so the particles are moving actually parallel to that axis as opposed to perpendicular. But again, we translate those longitudinal waves into transverse waves, so it's easier to interpret what's going on. So we'll take a look at what's referred to as constructive interference. In constructive interference, if we look at the top here, we're going to look at the purple wave moving to the right and the red wave moving to the left. And so they're going to be what are referred to as transverse waves. And what you want to think about is that these waves are made out of particles. And just like we talked about in the coil lab, the particles are going to be moving perpendicular to the axis. So the particles are going to be moving up. And remember that they are moving up because that's the way the energy is displacing them. So it's a displacement of the particles moving up, and then once that wave moves past, those particles are going to start moving back down, so they're going to be along the axis again. So as the wave passes over, particles move up perpendicular to the axis, and then they move back down. The energy is transferred through those particles. And so we would do the same thing for the red wave. You're going to have a series of particles, and the particles are going to be moving, again, perpendicular to the axis as the wave moves by. And then once the wave moves on, then those particles are going to be along the axis. So remember, the particles don't move from point to point along the axis. The only way they move is perpendicular. So as those particles move along, they're transferring that energy, and so those particles are moving up and down, and as the energy is being transferred, it's going to collide. And that's what happens in the second diagram here. And you'll see that this area here, right, which is representing the amplitude, is equal to the energy. And so we're going to have an amplitude of 2 by 4 for the red, and we're going to have an amplitude of 2 by 4 for the purple. And again, that amplitude represents energy, and constructive interference is just simply when the two waves collide. And at that moment in time when they completely overlap, you're going to have 2 by 4 for the red, 2 by 4 for the purple added together. They're going to be summed. And so the particles are going to stretch further away from the axis than they were when they're in their individual waves. And this would be referred to as constructive interference. And this would be two water waves coming together, and suddenly, if you're looking out in the lake and suddenly there is a much larger wave suddenly, that's just simply two waves coming together, summing those energies together, which pushes the particles up further from the axis. And then once those waves have collided, then the waves continue on. So the red would continue to the left, and the purple would continue to the right. So to summarize, constructive interference is when you have two positive pulses coming together. So in this case, we have two crests. You could also have two troughs, two negative pulses coming together. They are in phase because they're on the same side of the axis. And when they come in contact with each other, or completely overlap each other, they add their energies together. And since the energies are going the same direction, you get constructive interference, which means that the particles temporarily, at this point here, where they meet, they're going to, in this case, double the displacement perpendicular to the axis. Once the waves move across, then they just continue in the same direction that they were originally. The second type of interference is referred to as destructive interference. Destructive interference is when you have a crest and trough coming together. So you have a positive and a negative pulse, or you have them traveling out of phase. And again, the red is going to be traveling to the left, the purple is going to be traveling to the right. They're going to eventually meet, and they're going to meet at the center point here. And again, I want you to think of, in terms of energy, the energy direction, which is going to cause the force, is going to be moving in opposite directions between the purple and the red. So you're going to, if you kind of visualize, you would have particles, and we'll put a particle here, here, and here. These particles are almost in a tug of war, and we have equal energies going on both sides. We have the purple wave pulling this direction, and then we have the red wave pulling the opposite direction. And you're going to get that for each particle as they move across. And you're going to get, because they're equal energies in this case, you're going to get a net displacement that's going to equal 0. There's no motion. So actually what you see, even though those waves, those energies are present, you end up just seeing a flat line. And again, if you watch the waters of lakes, you have waves moving back and forth, and suddenly you get a calm area. That calm area is where you have destructive interference. And sometimes you have complete destructive interference, like this example, where you see a completely flat line. And again, that flat line is occurring at that moment in time because we have energies moving in the opposite direction. Those energies are causing forces to happen in the opposite direction. Therefore, you want to think of it as each particle as a tug of war, and they're neutralized because you have equal force going up, equal force going down. Net displacement is going to be 0. And just like constructive interference, the waves keep on doing what they're doing after their interference. Now I'm going to take you through 3 practice questions. And what I would like you to do is you're going to take a look at the practice situation. So again, we have a rectangular purple wave here, and then we have more of an upright rectangular wave to the right. They're moving towards each other. And what I would like you to do is draw this diagram, pause the video, and then draw what you think the final, or what's referred to as the resultant wave. And again, the resultant wave would be what happens when the red wave and the purple wave intersect. So when they perfectly come across each other. And so kind of what happens at that midpoint. And so I would like you to predict what you think is going to happen. And then once you've predicted it, then restart the video, and then I'll show you the solution on the next slide. All right, so the solution for practice question number 1, again, we would have the bottom here. This would be your initial wave coming from the left, and then this is going to be the red wave that was coming from the right. When you draw these, you always want to draw the smaller wave on top of the larger wave. And so you would see in this kind of pattern that there is only one area that you get constructive interference. The areas to the right and to the left at this midpoint would show no difference in wave pattern. So when you have different sized waves interfering with each other, then only specific portions of those waves will show either constructive or destructive interference. So this, if you're thinking now of sound, if we start applying this to sound, this would be two different frequencies coming together and producing a new tone or new sound, and because they would change the pattern of the wave, just temporarily. Practice question number 2. This is now going to be an example of destructive interference. But again, this is not a complete destructive interference. You only get complete destructive interference when both waves are identical in size and shape. In this case, they are different. And so we have a crest and a trough. So again, we have the purple going to the right, the red going to the left. And so again, I would like you to draw the setup, draw what you think is what it's going to look like when there is interference, and then you can move to the solution just to see if you're correct. The solution, again, this section here, right, this doesn't have any interference, so it's going to be like the original wave, the original purple wave. This is not going to have any changes. The only area that gets changed is the red square. And again, the red square is causing destructive interference. But it's only happening in a very specific section of the purple wave. And that's why you get this little change in shape. And again, if you change that or think of it in terms of a sound wave, you would be altering the sound of that wave. Because you've now changed the shape of it. You've changed the energy patterns. You've changed the frequency of that wave. So in this case, you would have, again, nothing would be changing on either side, the left or the right. The only spot that gets taken out of that original wave is the negative energy of that square. Again, it is pulling down, and if you go back to that original drawing, it is moving 2 squares down or 2 units down, and that's why you're getting 2 units down from the original wave, the purple wave. Okay, we're going to go through one more practice question. And that practice question is looking at number 3. So we're changing the shape of this. Something to note about this practice question, the shape of this pattern is, in terms of width, is the same, but definitely the height is different. We're looking at a rounded pattern, so you're going to try to sketch, again, what you think is going to happen in this outcome of this wave interference. This is going to be another example of destructive interference. All right, so we're going to take a look at the solution of this one. This one's a little bit more tricky, and sometimes it's hard to visualize what's going to happen. So I'm just going to focus on the lower diagram here and just show you, in terms of particles, what's happening. So if we take each particle here, so let's take a look at this one and this one. So this is part of the positive wave at the top, negative wave down the bottom. We can see that this is one full unit up, and this one is half a unit down. So it's almost, you're doing, if you want to think in terms of math, we have one positive unit of displacement of that particle, and we're going to add a negative 0.5, because that's going to represent the trough. So this is your crest, this is your trough, and what we end up with is a positive 0.5. So that means our resultant is going to end up right there. That's the net pull on that particle. If we sum the energies going up and down, which is also equivalent to looking at the forces going up and down, the end result of that, those two particles fighting in those directions, is this spot, so halfway up. And you can do that for the second one, right? So if we look at this, we are one unit down versus 2 units up. So this is going to be positive 2. That's going to be a negative 1. We're going to sum the forces, or sum the energy, and so we're going to end up with a positive 1. And that's going to occur all the way through. You could do that for each dot, and that is why we end up with a resultant that is lower than the original crest, but still a positive pulse. So we have a negative portion taken out. That negative wave makes the crest less positive, but it still ends up being a positive crest. And that's the way you'd want to approach a lot of your destructive and even your constructive interference. Pick specific points, and those points represent particles, and then you're really taking each point and finding the sum of the forces, the sum of the energy. And where it ends up is going to then create your resultant wave, which in this case would be our purple wave here. That is going to be our resultant wave of our constructive and destructive interference patterns. So for homework, there's some textbook questions listed in your notes. You want to go through those textbook questions. There's a few more drawings that you can practice. And then when you come back in on next class, we're going to do a little simulator. We're going to continue to practice these questions, and I'll show you, again, a little bit more detail on the board, how you can draw them out with those particles. So don't worry if you're not quite catching on with some of the little bit more tricky ones. We'll be able to break those down in the use of particles and displacement and the forces of those energies.